The forward dynamic resistance of a junction diode varies dash as the forward current. The dynamic resistance of a diode is given by eta Vt by IDC, which means the dynamic resistance is inversely proportional to the forward current. Inversely. A very, very simple question. The units, I can write units of Q by Vt are. See, we know Vt is equal to Kt by Q, whose units are volts. But what is given Q by Vt? So its units should be volt inverse. Next. In the circuit shown below, the ideality factor eta of the diode is unity and the voltage drop across it is 0.7 volt. Okay. The dynamic resistance of the diode at room temperature is approximately. See, at room temperature, means Vt is equal to T by 11,600. It is T is 300 degrees by 11,600. We know its value is 26 millivolts. Okay. Then what about IDC here? IDC is equal to 1.7 minus 0.7 by 1 kilo ohm. It is 1 milliampere. Then the dynamic resistance is equal to eta Vt by IDC. Eta is 1, Vt is 26 millivolts by IDC is 1 milliampere. Finally, it is 26 ohms. If you observe all the four options, it is close to 25 ohms. Okay, as it is mentioned as room temperature, at room temperature Vt value is 26 millivolt accordingly I wrote. Otherwise, default value of Vt is 25. In that context, absolutely you will be getting the answer as 25 ohms. A very simple question it is. In the circuit shown below, assume that the voltage drop across the forward biased diode is 0.7 volts. Okay. The thermal voltage Vt is equal to Kt by Q is equal to 26 millivolts. The small signal input Vi is equal to Vp cos omega t, where Vp is equal to 100 millivolts. Then the DC current IDC through the diodes. Actually, through the diodes I can write. And the second bit is the AC output voltage VAC is voltage across the output terminals, means sum of the voltages across all the four diodes. Okay, how to do this problem? See, first let us take with respect to DC. Let us consider the circuit with respect to DC. It is 12.7 volt, 9900 voltage across each diode is 0.7 volts. Then the current flowing is IDC. 12.7 minus 4 diodes, 4 into 0.7 by 9900. We get it to be 1 milliampere. 12.7 minus 2.8, it is 9.9 by 9900. 1 milliampere. A very, very simple thing. And so that, and they are also asking the AC output voltage, means with respect to AC we need to take. So first of all, what is RF? It is eta Vt by IDC. Eta is 1, Vt is 25 millivolt and IDC is 1 milliampere. It is equal to 25 ohms. Once you get RF, then let us take with respect to small signal AC. What do we get? You see, DC in the sense we are not showing any AC source. And with respect to AC means we are not showing any DC source. And as far as the DC circuit is concerned, the representation of diode is by means of an voltage source of value 0.7 volts. With respect to AC means diode is replaced by a resistance RF whose value in this example as 25 ohms. Okay. It is not at all superposition. While finding the DC currents and DC voltages, we are using only DC source. While writing AC currents and AC voltages, we are using AC source. But it is not superposition. Please do observe this. So, it is 100 cos omega t millivolts, 9.9 K. Now I can say this current is IAC, the total voltage is VAC. Okay, the total DC voltage is IDC. If you are interested to know, you can find it. It is 4 into 0 0.7, 2.8 volts VDC. They are asking VAC, not VDC. Further, what is the equivalent circuit? We can write, instead of each diode, we are writing RF. See, earlier I explained with respect to a single diode. Now it is with 4 diodes RF. 25 ohms. We can take this. And what about IAC? It is Vs by 9900 plus 4 into 25, 4 resistors. Vs, it is 100 cos omega t into 10 power minus 3 by 10,000. It gives us 10 cos omega t microamperes. Okay, we can take it this way. Once we get IAC, then VAC is IAC into 4 into RF. 10 cos omega t into 10 power minus 6 multiplied with 100. It is cos omega t millivolt or 1 cos omega t millivolt. We can take this one. See the options. Here option A is correct. And here 1 cos omega t millivolt. Okay, students may be getting doubt like earlier I mentioned Vs is some 20 millivolts. Now Vs is 100 cos omega t millivolt, 100 millivolts. Then what happens to the each diode? To be frank, all 4 diodes together are taking 1 millivolt. Means what is voltage across each diode? Out of curiosity, only I am writing AC voltage across each diode. it is equal to IAC multiplied with RF, that it is 10 cos omega t micro into 25. It is 250 or 0.25 cos omega t millivolt. Is it not far far less than eta Vt, whose value is 25 millivolt? Absolutely. In the previous problem, we have got voltage across AC voltage across diode is 0.375 millivolt. Now it is 0.25 millivolt, whose value is very much less in comparison with eta Vt. Even though the input is 100 millivolt, what is happening here? Maximum voltage can be seen across this resistor. Okay, all four diodes together are offering a resistance of 100 ohms, but this resistor alone is offering 9.9 kilo ohms. Obviously, out of 100 millivolt, 99 millivolts is across 9.9 k, and remaining 1 millivolt is across all the four diodes. Right? You can even write. So AC voltage across 9.9k is equal to IAC into 9.9 into 10 cube. It is equal to 99 cos omega t millivolt. This is how you can observe. Maximum voltage is across this 9.9k. Diodes are taking very less. Each diode, if you take, it is taking 0.25 millivolts. These are all additional observations, we can say. It's not like simply getting the answer and closing the problem. Every problem is very interesting. We understood some concepts, we learned some concepts, and we are cross verifying with what we have learned. Okay, this is how we can do this problem. Next, 56. In the circuit shown, if Vs is equal to 100 sin omega t millivolt, this is, and Rs is equal to 1k, Vt 25 millivolt, ideality factor is equal to 2. Find V output. Assume capacitors are very large. What is the meaning of capacitors are very large? Capacitors are very large means, anyway, capacitor acts as open circuit with respect to DC, whether it is small or large. And if it is large, with respect to AC, the capacitor almost acts as short circuit. Okay. Capacitor is very large. Impedance offered by the capacitor, if I take 1 by j omega c, capacitor is extremely high, so the overall impedance is extremely low, means it is almost acting like short circuit. That's the meaning of capacitors being large. Okay, so first of all, what we need to take, always you take two problems we did, it is a third problem. First, take the DC equivalent circuit, from which find the DC current flowing through the diode. From the DC current value, find the value of RF. Next, take the equivalent AC equivalent circuit and complete the remaining calculations. Okay, so first, with respect to DC, all capacitors act as open circuit. So, with respect to DC, it is open circuit diode, and this is also open circuit. Actually, to be frank, no current flows through this capacitor, it is in air. Okay. So, it is further written like, it is I, whose value is 1 milliampere. So, it is further written like, it is for the sake of students, for better understanding, I am writing it so. What is IDC? Its value is 1 milliampere. Once we get IDC, then I can write RF, eta Vt by IDC. Eta is 2, Vt is 25 millivolts, IDC is 1 milliampere. So it is 50 ohms. Every time so far we have seen 25 ohms because ideality factor was given as 1. Here it is given as 2. Accordingly, we are getting RF. Okay. Next, let us take with respect to AC or with respect to small signal AC. What can we write? We need to remove all the DC sources. With respect to small signal AC, all DC sources should be made 0. If it is current source, open circuit. If it is voltage source, it is short circuit. It is made 0 means here we have a current source 0. And one more thing is all capacitors act as short circuit. Okay, so here I can take the diode. Next, RS and one capacitor, it is acting like short circuit. One kilo ohm. And one more capacitor we have here. V output. First of all, is there any signal that is possible here? No. So whatever the voltage you have here, the same voltage can be seen here. So V output can be seen here. Okay. This will definitely there is a possibility for current to flow through this capacitor C1, which acts like short circuit. C2, what can we write? No current is flowing through. When no current is flowing through the impedance, and before and after the impedance, you can see the same voltage. Now, what is the equivalent circuit of the diode? Instead of the diode, we can write by means of its RF, whose value is 50 ohms, 1 kilo ohm. Yes. Okay. This is our equivalent circuit. And what are they asking? V output. Simple voltage division rule. V output is equal to Vs by 1 kilo ohm plus 50 multiplied with 50. And what about the Vs given? 10 sin omega t millivolt into 50 by 1050. 5 cancel. So 21, 10 by 21. So you can see 0.46 approximately 10 by 2. Actually 10 by 20 means zero point 0.5. So instead of zero point 0.5 we can see less than zero point 0.5 now, 0.476 sine omega t millivolts. That's it. Okay, this is how we can find. Here I can write IAC, V output, and of course it is AC. Okay. Next question. Find the value of the ratio V output by V input if I is equal to 0.25 milliampere. I means this one. It is 0.25 milliampere. Assume capacitors are very large. Okay, these two capacitors are very large. That's it. Right. Okay, then let us take with respect to DC. Okay, so if I take with respect to DC, 0.25 milliampere. And this capacitor with respect to DC means it is open circuit. We remove the AC signal, we input. And what about this capacitor C2? It is in air, right? If you have some resistor, then I can say that there is a possibility of the current as it is, then it is open circuit. But here no resistor is present. So what we can do simply, even though we have this capacitor, right, no current is possible here. Simply, right, instead of saying open circuit and all, what we can say is as it is in air, no current flows through it. This is diode D1, D2. This is open circuit. It is neither open circuit nor short circuit. No current is flowing and there is no charge across the capacitor. I can say short circuit only. Even though it is short circuit, no use because it is not completing the path. Okay. Then what is the equivalent circuit? This is equal to ID1 because it is diode D1. Diode D2, this current is ID2. It is 1 milliampere. So 1 milliampere is coming this entering this node. 25.25 milliamperes is ID1. So ID2 will be equal to 0.75 milliampere. Now we have got ID1 and ID2. From that we can find RF1 and RF2. RF1 is equal to eta Vt by ID1. Eta they have not mentioned. Ideality factor by default we take it as 1 and Vt they did not give, we take Vt as 25. So 25 millivolt by 0.25 milli. Milli and milli cancel and it is 100 ohms. Next RF2, it is again equal to eta Vt by ID2. It is again 25 milli by ID2. How much it is? 0.75 milli. It is equal to 33.33 ohms. Okay. 100 by 3, 33.33. ID1, ID2 have got. Next, let us find, take the circuit with respect to AC. Okay. What can we write with respect to AC? With respect to small signal AC, what happens? All DC sources, I have written it already in the previous problem, are made zero. As it is mentioned, capacitors are very large. C1 acts as short circuit and C2 does not play any role. It is also short circuit only because no current is flowing through C2 and there is no charge accumulation. Default we take it is right with the zero initial conditions. Okay, voltage across the capacitor C2 is also 0. No current is possible through C2. Okay, and C1 and C2 act as short circuit. So remove the current source first. Okay. Next, VI C1 short circuit. Next, diode D2. Next, current source is 0, so it is open circuit. See what we have here, another current source, it is open circuit. Oh, sorry. I redraw the circuit. Here we have a capacitor which acts as short circuit. Next, V input. Here we have a current source which is again acting as open circuit. Diodes D1 and D2. This is our output. Okay, we have removed the DC sources. Current source means open circuit, voltage source means short circuit. That's what we do. D1 and D2 are in conduction. And here also, to be frank, we have one more capacitor C2 which acts as short circuit. So finally what we can write, D1 D2 V input and V output. Okay, I hope you understand this. It is open, so, and this is also open. The resistors sorry, diodes are appearing in series now. Then replace the each diode by means of its equivalent resistance. RF1, whose value is equal to 100 ohms. RF2, it is equal to 100 by 3 ohms. V output, it is also ground. So what is V output in terms of V input? V input by RF1 plus RF2 multiplied with RF2. Then gain AV is equal to V output by VI. It is equal to 100 by 400, or it is equal to 0.25. That's it. Okay, next. In the circuit shown in figure, the diodes D1 through D4 are identical. Each has eta ideality factor of 1 and is a 1 ampere diode. Means with respect to DC, the current through each diode is 1 milliampere. That's what it means. That is, it exhibits a voltage drop of 0.5 volts at 1 milliampere current. Okay. For small signal input voltage, example 10 millivolts peak means 10 sin omega t or 10 cos omega t, like that. Find the values of small signal transmission V output by V input. What is the gain of the circuit? They are asking. As usual, let us take the circuit with respect to DC. With respect to DC means AC sources should be removed, but not superposition. So let us take with respect to DC. Here it is given as some 10 kilo ohm resistor. And what about this one? AC source is 0 means it is short circuit. Okay, and each diode is handling a voltage of 0.7 volt. So that what is the current through each diode? It is 1 milliampere. 1 milliampere and 1 milliampere means it should be 2 milliampere. Okay, and if you observe this, it is like a balanced bridge, identical diodes. Okay, and each is offering voltage of 0.7 and 1 milliampere current. If that is the case, it is looking like a balanced bridge. So balanced bridge means here this voltage should be equal to this voltage. So no current is possible here. IL is 0. Then this voltage will be, if I take VA, it is 0, and this voltage VB is also 0. Anyway, 1 milliampere, 1 milliampere are flowing through D1, D2, D1, D3. D2, D3 also carry the same current. So that again this is 2 milliampere. This is the equivalent circuit actually, as far as DC is concerned. Okay, it is a balanced bridge we can take. So then what about RF eta Vt by IDC? So ideality factor is 1, Vt is 25 millivolt by IDC is 1 milliampere. So see, almost all the problems we are getting RF as the dynamic resistance of the diode as 25 ohms. Only once we got 50 ohms, where eta was given as 2. Okay, then let us take the AC equivalent circuit. With respect to AC, this is open circuit, this is open circuit. Okay. DC sources are removed. Open circuit should be 0, means current sources will act as open circuit. This is how we can see. Now we can replace each diode by means of its equivalent resistance. So further, I can write the circuit. V input. Okay. Then if you see again from this direction to this direction, if you see it's a balanced bridge. And in a bridge, balanced bridge, if all resistors are equal, it can be represented by means of a single resistance, which is equal to the resistance offered by a particular R. So 25 ohms. In networks, we are well aware of it. Otherwise, also, these two are in series, these two are in series. So series means total 50. Here also it is 50, 50 parallel 50, it is 25. So ultimately, I can write here 25 ohms, 10 kilo ohm, V input, V output. What are they asking? The gain, or V output is equal to V input by 25 plus 10k into 10k. Our gain AV is equal to V output by V input is equal to 10,000 by 10,025. right? Almost it should be equal to unity, or I can write 0.99, close to unity. It comes around 0.9975, something close to 1. Okay, this is how we can do the problem. Next, see this. In the circuit shown in the figure below, I is equal to 1 milliampere is a DC current and Vi of t is a sinusoidal voltage with small amplitude of millivolts. Representing the diode by its small signal resistance Rd, which is a function of I, sketch the circuit for determining the output of t and thus find out the cutoff frequency Fh, assuming Vt is equal to 25 millivolts at room temperature. Okay, how to do this? Let us take the circuit first with respect to DC. Here, this AC source acts as short circuit and capacitor acts as open circuit. That's it. It is 1 milliampere. So, what about IDC? DC current flowing through the diode 1 milliampere. So, the dynamic resistance RD they mentioned, okay, RD or RF, it is eta Vt by IDC. It is 1 into 25 milli by 1 milli. You see, in all the problems we are getting the dynamic resistance as 25. So, they are giving like this what to do. Okay, right. Then sketch the circuit for V output and thus find the cutoff frequency. Okay, let us take with respect to AC. With respect to AC, this is open circuit and the capacitor is given as 10 nanofarad. It is very small. They are not saying very large. It is very small. 10 nanofarad. It is there. It is not mentioned very large. Large in the sense hundreds of microfarad or millifarad or farad. Okay, it is given in nanofarad. Sorry, we can't neglect it. We cannot take the capacitor as short circuit. So, with respect to AC, current source open. Next, diode and V input. Next, this capacitor. V output, it is 10 nanofarad. Okay. Further, it can be redrawn like this. Diode forward resistance, AC input, V output. It is now looking like a low pass filter. Okay. Then at higher and higher frequencies, right? Anyway, it's a low pass filter. What is the cutoff frequency? Upper cutoff frequency they're asking. As the circuit is behaving like a low pass filter, what about its cutoff frequency? Okay, FH is equal to, I'm directly writing the answer. It is 1 by 2 pi RF into C. It is 1 by 2 pi. RF is 25 ohms and capacitor is 10 nanofarad. So its value is equal to 500 1 by 5 pi into 10 power 7. Approximately I'm writing, I can multiply and divide with pi. So pi square is 10. So 2 pi. 2 pi means 2 pi into 10 power minus 7. Pi is 3.14. So 6.28 or 0.63 I can write. Approximately 0.63 meg. Sorry. It is 10 power 7 megahertz. Like this we can write. It is looking like low pass filter. With FH is given by this. Okay. Next. A DC current of 26 microamperes flows through the circuit shown. The diode in the circuit is forward biased and it has an ideality factor of 1. At the quiescent point, the diode has a junction capacitance of zero point 0.9 nanofarads. Its neutral region resistance can be neglected. Assume that the room temperature thermal voltage is 26 millivolt. Instead of 25, they give 26. For omega is equal to 2 into 10 power 6 or 2 mega radian per second, the amplitude of the small signal component of the diode current in microamperes corrected to one decimal place is. Okay. Small signal model and it's a high frequency response, I can say. Okay, actually, if you take a PN junction diode at a, it has an internal junction capacitance. We know that, right? If you take a PN junction diode, the junction, right? Here we have a junction capacitance in the order of nanofarads to picofarads, whose effect cannot be observed at low and mid frequency range. Its effect can be seen in the frequency range of megahertz. Okay, nanofarads capacitor, nano or picofarads. So the junction capacitance, effect of junction capacitance can be seen only at in the frequency range of megahertz, not in hertz or kilohertz or even hundreds of kilohertz. Okay, so that's very important point. Here I'm writing effect of junction capacitance of a diode can be seen at high frequencies, right? Generally in the order of megahertz or mega radian per second. At low frequencies, what I meant to say is, suppose, right, you take a junction capacitance. Here it is given in this problem 0.5 nanofarad it is given, right? So if I take XC is equal to 1 by omega C, 1 by omega into or 2 pi f into C, anything we can write, not an issue. 2 pi, suppose f is equal to some 10 hertz and the capacitor is 0.5 nanofarad. What do we get? If the input signal frequency is 10 hertz, then XC is equal to 1 by 2 pi into 10 into zero point 0.5 means 1 by 2 into 10 power minus 9. 2 cancel. It is 10 power 8 by pi. You can imagine how much larger. Is it not a like okay, if I multiply and divide with pi, then pi into 10 power 7 heads. You can get it. Sorry, ohms, magnitude wise, if you take it, sorry, 10 pi mega ohms. We can see, of course, if it is hertz, then if it is 1 kilohertz, then XC will be equal to, so instead of 10, I am writing 10 cube. So in the numerator, two zeros will be reduced. XC will be equal to 10 power 6 by pi. It is also high impedance. If you take 1 by pi mega ohms, it is high. Suppose frequency is equal to 1 megahertz, then XC is equal to not 10 power 6, instead of 10 power 6 I am writing. So it is a 10 cube by pi. Okay, if it is 10 power 6, then it is 1000 by pi. Means the effect of the impedance offered by the capacitor can be observed only in the range of megahertz, not in kilohertz or hertz. Okay, so that's why what we do, impedance is extremely high at low frequencies, means it is considered as open circuit, and here also it is considered as open circuit. It is not short circuit, some appreciable value we can see. Okay, the effect of the junction capacitance can be seen at a frequencies of megahertz, not in hertz or kilohertz. Then what is the equivalent circuit of diode with respect to small signal? Strictly speaking, the equivalent circuit of diode is like RF in parallel with this CF, forward resistance. Its effect CF is not considered so far because it almost acts as open circuit uh, by default. But in this problem, the mega radian per second frequency is given so that the capacitor is not acting as open circuit. We need to consider the impedance offered by the capacitance into consideration. So with respect to signal, small signal, this is the, so Z, I can write this whole thing as Z, where Z is equal to RF into 1 by CS by RF plus 1 by CS. It is RF by 1 plus S RF into C. C I am writing instead of CF. S is equal to J omega. If I substitute the values of R, RF, it is given as sorry. We need to find it, of course. Yes. Okay, let us find all those things. Not a big deal. Or RF by 1 plus J omega RF into C. Okay. With respect to small signal, this is the equivalent circuit. But till the last problem, I wrote only RF without considering the internal junction capacitance of the diode, whose value is by default taken as open circuit at low and mid frequencies, whose effect can be seen only in the range of megahertz of frequency. As in this problem, that frequency range is given, input frequency is given as 2 into 10 power 6 radian per second. I am not considering this capacitor as open circuit. I am taking its impedance into consideration. Okay. So how to find RF? Let us take the circuit with respect to DC. Right. Even without writing, they gave the DC current value 26 microampere. If I take this current as I suffix D, which is IDC plus IAC, IDC is 26 microampere. RF, I can write directly. RF is equal to eta Vt by IDC. Eta is one ideality factor. Vt in this problem, it is 26 micro. Is given IDC is 26 microamperes, I think. Write it down mistake. This is milli and this is micro. Which gives us 1 kilo ohm. Okay. Then what about Z? It is equal to RF 1 kilo ohm by 1 plus J. Omega is 2 into 10 power 6 and RF is 1 kilo ohm and CF is 0.5 means 1 by 2 into 10 power minus 9. 2 and 2 cancel. It is equal to 10 cube by 1 plus J. I can multiply and divide with 1 minus J. It is okay. A plus B into A minus B, 1 plus minus of minus 1 plus 1, 2. So it is 500 into 1 minus J. I can. Then let us take with respect to AC. This circuit with respect to AC. I should remove this DC source and take the remaining. Okay. That DC source I am removing and right AC source 5 sin omega t millivolt and 100 ohms. Instead of diode, what you can write? V input. Okay. RF and C. Instead of RF parallel with CF, I am writing it by means of Z. Magnitude of this current is asked. So what about I? Here it is V input or VI. Okay, V input by Z plus 100. V input is 5 sin omega t millivolt by Z, it is 500 into 1 minus j plus 100. Okay, it is equal to 5 sine omega t into 10 power minus 3 by 500 plus 100, it is 600 minus j 500. Okay, it is sine omega t into 10 power minus 3 by 120 minus j 10. 12 minus, okay, 120. Okay, magnitude of the current means what we can write 1 by square root of 120 square plus 100 square. Okay, if you calculate it, so we can see 6.4 microamperes. I'm again writing the answer directly. Okay, this is how we can do this problem. Here their concern is to understand the effect of internal junction capacitors. Anyway, it is called high frequency response of a diode. Even the same story we study in BJT, FET as well. High frequency response of diode, high frequency response of BJT, high frequency response of FET, low frequency responses, mid frequency responses, all these things. Right? That's it. So they are asking the amplitude of the small signal component of the diode current in microamperes corrected to one decimal place. Amplitude means it is 6.4 microamperes. That's it.